So now let's solve the same question using work energy theorem, right? Work energy theorem. So to do this question using work energy theorem, first we should understand what is work energy theorem. It simply states that work done by a force should be equal to change in kinetic energy of the body, right? So since this F is acting at an angle theta, we should first identify which component of this force is doing the work. Okay. So this force F is equal to 2 Newton can be resolved into two components. One is the horizontal component, right? One is the horizontal component and two is the vertical component. And two is the vertical component. Now, which among them are doing the work? See, since the object is moving only along the x direction, right? Since the object is moving only along the x direction, which essentially means that since, say, if you consider now, most of the students get a doubt here. Let me just clarify this. So if there's an object over here, okay, there's an object over here, and this object is moving only along the x direction. It is not moving along the y direction. It is restricted to move along the x direction. It is restricted to move along the x direction. There will be displacement only along the x direction. Since it is not going up, nor is it going down, I can therefore say that the displacement along the y direction is equal to 0. If you differentiate this equation on both sides with respect to time, we can say that velocity of the object in the y direction is equal to 0. Differentiating again, acceleration in the y direction is equal to 0. Now, if you multiply this with m on both sides, m into ay is equal to 0. What is m into ay? M into ay is fy is equal to 0. And if fy is equal to 0, what will be the work done by this force, fy dy? So Fy dy will also be equal to 0, which means work done by the force component in the y direction would be equal to 0. Which means when we consider work energy theorem, we need to consider only the x component. Okay, I hope the logic and the concept is clear here. If that is clear, let us now understand the application of work energy theorem. Okay. So please excuse me for a second. Let me just make it a bit more legible. I'm sorry for the less font size here. I'm really sorry. Okay, so while we use the work energy theorem, what is work energy theorem? It according to the work energy theorem, the work done by the force Fx, this time it's been more specific, Fx, on the object over a distance x, right? So this is the distance moved by the object over a distance x, will be equal to increase in this kinetic energy. My bad, it is not increase, it should be change in kinetic energy. Otherwise I can write that work done by the x component of this force Fx is equal to delta Ke, which is equal to Kf minus Ki, right? Now what is Kf, kinetic energy of this object at this position, right? So here the velocity is v, and in this early position the velocity is u. Why? Because it was at rest. And since the velocity is u, what is the kinetic energy? It would be half m u square, which is equal to half m0 square, which is 0. Therefore, initial kinetic energy is equal to 0, which means change in kinetic energy would be Kef minus Kei, and this Kei is now equal to 0. Therefore, we can say that delta Ke is just equal to the final kinetic energy, which is nothing but the work done. Okay, right? So I hope the way we are arriving at this steps are clear. If that much portion is clear, now we can find out the actual work done. While we find out the work done, what we'll do is we'll find out the work done by the x component over a small displacement, right? Over a small displacement. So which essentially means say this much is dx. Okay, and then we'll integrate this from x equal to 0 to x equal to x. Okay, so we can say that the work done by the variable force Fx is equal to 2 cos kx would be equal to, over a small displacement, dx would be equal to dw is equal to fx dx. What is fx? Fx is 2 cos kx. What is the limit? Would be from 0 to k. So 0 to x. So x varying from 0 to x. Work done would be from 0 to w, right? In which case, we can say integral of dw is w, integral of cos kx is sin kx by k, right? K is a constant. Now applying limits, upper limit sin kx at x is equal to sin kx at 0 is equal to sin k into, instead of x here, what do we have? Instead of x we have 0. Now what is sine 0? Sine 0 is 0, which means this term will get eliminated, right? And then we only have one term. W minus 0 is w, sine kx by k into 2, right? And now we have w is equal to 2 by k into sine kx by k. What is kx? Kx is theta. Now what is this work done is equal to? Work done is equal to change in kinetic energy. Change in kinetic energy is kinetic energy final here. Why? Because kinetic energy initial was 0. And according to the question, it is given that the kinetic energy of the object would be E by nk sine theta. So, sorry, E is equal to n by k sine theta. So I can write here kinetic energy final, or in other words, I can write that this is equal to E is equal to n by k sine theta. Now when you compare these two equations, we got sine theta, k, which means the only unknown variable is n, which is equal to 2. Therefore the value of n would be equal to the value of, not x, the value of n would be equal to